In this video, we're going to use the Weierstrass substitution, which is t equal tangent of x over 2, to evaluate this particular integral involving a rational function of sine and cosine. As long as you have first degree sine, first degree cosines in the denominator, it's going to work great. Not convenient if it has something in the numerator, but on some occasions it does work. Here we don't have the standard u substitutions are going to work. If I let u equal to the denominator and take the derivative, I don't get what's in the numerator. So what this technique is going to do is going to allow me to write this expression in terms of a rational function of the variable t. Then you can use other techniques like partial fractions, decomposition, and so forth. So let's look at this. You don't really have to know how this is derived, but it might help you to understand it. We start off with this substitution. Tangent of x over 2 is t, or I can write that as t over 1. And then we form this right triangle here. Here's your angle x over 2. Tangent of that angle is opposite over the adjacent. That, of course, is definition of tangent. And from that, we can get the length of the hypotenuse here. Square root of 1 plus t squared. So from the diagram, sine of x over 2 is opposite over the hypotenuse. So that's t over square root of 1 plus t squared. And then I want a representation for sine of x. So using the double angle here, sine of x is equal to sine of 2 times x over 2, like 2 theta. And there's an identity that tells me that this is equal to 2 sine of x over 2 cosine of x over 2. So from this here, this is 2 and sine of x over 2 opposite, which is t over the square root 1 plus t squared. And that's times the cosine of x over 2 here, adjacent over the opposite, so it's 1 over the square root of 1 plus t squared. Let's multiply 2 times t times 1 gives me the 2t here. Radical 1 plus over 1, the square root of 1 plus t squared times the square root of 1 plus t squared gives me, radical cancels, I get 1 plus t squared. And notice for cosine of x can be written as cosine of 2x over 2. And then I have this identity from trig. So the cosine of x over 2, adjacent over the opposite, put it in there. Of course, you have the minus 1 combined, just the algebra there. You get cosine of x is 1 minus t squared over 1 plus t squared. So in other words, we get a representation for sine of x in terms of t, cosine of x in terms of t. And then over here, we also need a dx. So for this one here, we take the arctangent of both sides to isolate the x over 2, and then we take the derivative, and we get a representation for dx, t over 1 plus t squared dt. So when you're working a problem involving sine and cosine, these are your main formulas you're going to use. For dx, you're going to replace it by this. For sine of x, you're going to replace it by this. For cosine of x, you're going to replace it by this. So everything's going to be in terms of t. You do the regular integration, it might involve natural log, it might involve partial fractions, but once you get your answer in terms of t, you can go back and just plug in wherever you see a t, you put tangent of x over 2, and that's going to be your answer. Now in our case, we have a definite integral, so we get the answer and then we just evaluate. So I'm going to leave the integral, the limits of integration off for now, because I'm going to change the variable here. So here's the way it works. It's going to be 1 plus, we need a replacement for sine of x in terms of the formulas I just showed you. So for sine of x, it was 2t. So replacing the sine of x by the formula we derived here, 2t over 1 plus t squared. And then for cosine, it was 1 minus t squared over 1 plus t squared. And for the dx, it was 2 dt over 1 plus t squared. And then we simplify. The 2 dt will go on top, and then the terms in the denominator will be multiplied by 1 plus t squared. So it'll be 1 plus t squared times 1 over here, be 1 plus t squared. For this one here, the second one, 2t over 1 plus t squared, the 1 plus t squared will cancel, leaving with 2t. For this third one here, the 1 plus t squared cancels again. I'm left with 1 minus t squared. And notice here, t squared and a minus t squared cancel. I got 2 dt on top there. And then we have 2t in the denominator left, plus 1 and a 1. So it'd be 2t plus 2. And then we can divide out the 2's. Cancel the 2 on the top, and these 2 will divide out. So that 2 cancels to 1. This 2 cancels to 1. This 2 cancels to 1. And then we would integrate this then in terms of t. So you got dt over t plus 1. That's like du over u plus 1. That's your natural log here of absolute t plus 1. Now, if this wasn't a definite integral, then you would just plug in the value of t. T is equal to tangent of x over 2. So your answer would be the natural log of tangent of x over 2 plus 1. And of course, there you'd have your constant of integration. And that would be it. That would be your answer in that case. But we have a definite integral here. Evaluate from 0 to pi over 2. So let me take this off here. And so I'm going to evaluate this then, not from 0 to pi over 2, because here, this corresponds to x. This would be x equals 0, x equals pi over 2. But we now have the variable in terms of t. Now, I could change the limits of integration here, or I could just leave the limits of integration. This would be 0, 2, this would be 0, pi over 2. But if I do it that way, then I would have to rewrite this as the natural log, go back to the original variable, say t is tangent of x over 2. This will now be evaluated from 0 to pi over 2. So again, I could keep the original limits of integration as long as I go back to the variable t here. So what does this come out to? I still need a plus 1 here. So it's natural log of absolute tangent of x over 2 plus 1. So if I plug in pi over 2 there where the x is, pi over 2 divided by 2 is pi over 4. So that would be 1. And then 1 more will give me 2. So this would be natural log. Don't need the absolute values because it's just positive. So pi over 2 there divided by 2 gives me pi over 4, which is 45 degrees. The tangent of 45 degrees is 1, and then a 1 plus 1 gives me a 2, and then it's a minus the value at 0 here. So put a 0 there. 0 over 2 is 0, so the tangent of 0 is 0, and then 1 more. So the tangent of 0 is 0, and then you have 1. So it'd be the natural log of 1, but that's 0. So the answer comes out to natural log of 2. And if they want an approximation, you can use your calculator. Now, if you don't go back to the original variable, then you have to change the limits here. Thanks for watching, and we'll see you next time.